situation. We talked about it briefly. I guess kind of like the two places where like I have some additional instructions. I guess like there's the, did I share with you the project report kind of instructions from last year?
Mm-hmm.
Some people say yes, some people say
No.
okay, so maybe I should do that. But basically, they're in principle just like what you have already written. That's a good start to continue on. Like, don't erase anything. Just build upon that part, and basically, it would be good to have like a little introduction, like a motivation, like why you're doing what you're trying to do. Then maybe, as I said, like 3 or 4 papers that do similar things, and like what I usually do is in the related work section, I would just take in the related work section I would just say, okay, this is this paper, they do this. They have this approach, this performance, but something that they're lacking might be this and that. So like you just basically acknowledge why you're different than they are, but this is like not necessarily required for this iteration. But like if you write a scientific paper, you have to show like why this is novel. But if you're like just doing some basic approaches, just motivate why you choose their work as a related work or a piece for information. Then you would describe your methods and or data set. You can like change that around. If you're more interested in like analyzing a data set, I think you would focus more on the data set, describe the data set early on. If you're more interested in like highlighting some methods, you would probably do the methods first. And then you're basically describing like your experimental setup, and that can be a plan for now, like where you basically just say, okay, I'm going to split up my data, this like training, test, and validation. I'm gonna validate for all these parameters and compare the approaches using these metrics. That could be like an experimental setup plan. It doesn't have to be like fully done yet. And then for some results, I would just like give a little bit of a results section, whatever you have evaluated so far. And for the next iteration, we would then like finalize both the experimental setup and the results section, and add a little like conclusion or discussion at the end. So what you find. So that's kind of like for now. The intro and related work and data set description and method description should be kind of final, and then towards the end of the paper you could like have more of a plan and like preliminary results, and then the next step would be to finalize that last part. Yeah, I hope that is more or less clear. It should be like building upon what you have, and that's why I kind of like wanted not to have like just bullet points, but more like a text. Yeah, so if it should be more of a like a free flow or readable text rather than like bullet points. And then you can like give examples and figures and stuff like that, but that will be just adding to the understanding of what's going on. I mean, if you have like a picture of like your method and this is what we're gonna do, like you can for example visualize the experimental setup with the evaluation at the end, and the data pre-processing, splitting it, training these classifiers, validating for these parameters, and then at the end like some metrics to evaluate. So that's kind of like the idea, right? Cool. And then we're going to have like a little progress report on Wednesday next week. So that everybody's preparing like a 5 to 10 minute kind of presentation. And everybody should like try to have some questions for it, if you will. Okay. So we talked about, last week we talked about hidden Markov models, and I'd like to wrap this up today. In general, we said that hidden Markov models are quite good at classifying everything that, or like modeling everything that's kind of like related to like sequences. Sequences in general could be, for example, words in a sequence, forming a sentence, speech, that like where dependencies between consecutive phonemes, for example, in the vocal tract, give you some additional ideas and hints to like what is represented, what is being said for automatic speech recognition, for example, and then other areas where you would want to basically identify, for example, if a car goes to the right, so it takes a left, like a right curve, or it takes a left curve. If you just get a picture of the car at each time step, you don't really know like what's happening. So you might be accelerating, you might be decelerating, and if you don't have access to the sequence, you can't really assess those kind of parameters. So, for example, velocity change, you would have to have like sequence information. Obviously, you can get that from static inputs as well. If you, for example, design your features to capture temporal dependencies. Does everybody know like how you would kind of try to do that? So if you have a speech signal, for example, like over a couple of seconds, and you wanted to somewhat characterize basically the dynamics of, let's say, the second formant here. That's like the second band that you see through here. Or you can characterize it over the second by, for example, saying first of all the mean value. Okay, but that doesn't really, like it's probably somewhere here, but for any normal sentence I would say the mean value of the second formant would always be somewhere around here. But you could, for example, also look at the standard deviation. So that gives you somewhat of an idea of like the range. You can use the upper and lower quartile, so the 25th percentile and the 75th percentile gives you like a range where it mostly is located in. And then you can do like first derivative, second derivative, etc. Like first derivative gives you like a slope. Is it going up or down over time? And the second derivative, is it like changing a lot over time? So that's kind of like this sort of information that you could also capture from a sequence while not employing a sequence classifier. But always, and in like as always, if you summarize something down to like just a few parameters, you're always losing some information, right? So that's why hidden Markov models still, if you get like every single time step, you can get informed over like the sequence of times, like what's happening previously, and you can make better predictions. And obviously, like the further like you look back, or the further you're able to look back, the more information you have. That's kind of like the difference between hidden Markov models, how we're using them. In our case, where we say, this is like the Markov process characteristic, where we say that the next step is only dependent on the previous step, so our look-back range is 1, but we could build hidden Markov models that have a further look-back range, so to say, but then we get into like very difficult modeling lands, and like it will, the hidden Markov models are just not great at doing such long look-back ranges. And then we're going to talk about like classifiers that actually have very, like particularly long look-back ranges, which are the long short-term memory neural networks that are quite popular these days. So, and then we'll see like why they actually have this characteristic that they can look back so far. So, but basically, because hidden Markov models aren't as strong in their modeling capabilities, they are not as strong as long short-term memory neural networks in speech recognition, and they were kind of like replaced by now, so nobody really is using them for that anymore. but yeah, so they have a very important point or like place in the history of machine learning. That's what we're talking about then. Okay, so this Markov process thing is clear to everybody, right? Okay, we had some examples, and chess was one of them. Then we started off with discrete Markov processes. Basically, one of the important aspects is, and this is kind of like required for all the models, we need to kind of know the probability to move from one state I to the next state j. So we need to have these probabilities, and we kind of say like once the network is once the model is trained, we don't touch those anymore. So this is kind of like a static form from then on. And it's important that like the sum over the rows basically always adds up to 1, so that like once you're in a state, you always go somewhere else, or you stay in the state, but something happens, like you're after the discrete time step, you cannot just be in limbo, for example. All right, and we talked about an example here where we added an additional probability here for each state to start in, and what often happens is if you have a 3-state hidden Markov model that you define, this is kind of like one of the things that people do. It's basically you define your hidden Markov model with like 3 states, and you allow to move from left to right, but you also allow to stay in the same state, and you basically never allow the network to start here, right? So you or the model to start here, so you always start at this location, so this is kind of like your entry point, and this is something that happens a lot, and this is always your exit point here, okay? And you can imagine this to be like a start and end point in the model. So once you're here, you always go into this state, and once you're here, you always end. Like there's nowhere to go from there on. And then this basically just means that your initial probability vector to start in one of these states is 1 and 0, 0, and then the Aij is then kind of like a diagonal matrix where you can walk. So you would have value here. So this is the A11, A22, A33, and then A12, A23, and this is 0 here, and then you have a bunch of other zeros. So you only allow transitions in one direction, and everything else would be zeros. So that's kind of like to make it easier for us, so the entire transition matrix is not necessarily always filled. So you don't have to have all these values all the time if you define your hidden Markov model that way. And so in this case, we can see that from every point I can move to every other point, okay? Or like from every state I can move to every other state. So I can stay in this state, I can move to this state, I can move to that state, okay? So that's kind of the idea of those. And we have that in slides as well, what I just draw here. Okay, so that was an example here. But then we talked about observable Markov models where we basically observe a state sequence, and we can calculate the probability of such a state sequence, and note that here the observations are states, so Q's, and in the other case there will be news, like where you just have observations and the states are hidden, so we don't see those. But in this case we can calculate the state sequence very easily because given our Markov property, each position, or each transition is only dependent on where you are right now. That means you can start off with a pi here, and then you just multiply all the transitions there, and should be fairly easy. And we had an example with some balls where we had these transition matrices. So if you only wanted to move from one state to the other, you just put those zeros here, and then you have to update this as well, because it needs to sum up to 1 still, right? Like even if you have zeros here. Then we can generate any sequence, but obviously, like, so we want to calculate the probability, and it's fairly easy to do so with those simple observable Markov models, okay? So one of the things that we need to understand now is so how do we get to like have this model? Like how do we build the model, and we build the model using k sequence of length t. So we want to have training data that has just these observations, or like basically we have our training data, and we can derive from our training data the probabilities to start in a state, to end in a state, and to like transition from state to state. And that's basically done through maximum likelihood estimation, where the start sequence, the starting point pi I probabilities are just calculated over like how many times do I start in each state divided by the number of starts that I have. So that should be fairly trivial. And then for the transitions, we basically count all the transitions that we have from I to j and divide by the sum of the times we were in this state. So that should be fairly clear. And then, so here, and this is kind of like the analogy that we had previously with the maximum likelihood versus maximum expectation maximization. So the EM algorithm versus the maximum likelihood estimation. This is, so to say, like the observable case, or like the supervised case, and the hidden Markov model will be like the unsupervised case. We talked about that before. And the hidden Markov model, we can't directly calculate these anymore, but we have to calculate them through expectation maximization. We're gonna get to that today. All right, so let's move on to the hidden Markov models. In this case, we don't observe states because those are hidden, obviously, but we observe observations, and those observations in this case are some, like, it's a discrete set of possibilities. It could be red, blue, green, something like that. Okay, so a type of color. But so if you do speech recognition, for example, these observations could obviously be continuous, and instead of like instead of modeling a probability of like observing one discrete state, you would try to model what the probability is of a continuous input. Okay, but that just changes your like the state modeling from like the modeling of the observation probabilities from a simple like discrete model to like a Gaussian mixture model, for example, where you can have continuous data. All right, so the new variable that we need in this case is bj, which is the probability of observing a certain like observation nu m, given that we are in state j. Okay, and in this case, so like now we don't observe the states; we observe observations, and yeah. So that's kind of like once you have trained a neural net, like a hidden Markov model, you can generate any sequence of observations. So like because you can sample from your states as well, but that's not really like what we're gonna do most of the time with hidden Markov models. But that basically gave them their name of like being a generative model, so they are able to generate sequences, but we're using them for classification. So we talked about our example now. Like now the orange have all the colors because each state can have a probability of producing all the observations that are possible. Obviously, like you could have states that don't have a probability to produce like a green ball or something like that, but you can model that. And so all the urns have now different colored balls in there. But however, you don't see the urns anymore. They're behind a curtain, and like you only see the observations at each state, and you basically from then on try to understand which state sequence we have observed.
Do we know how many urns there are?
Yes. Yeah. So
So
you know the number of
we
urns.
come up with the potential states.
Right. So and then we're going to get back to those three basic problems. But the first two basic problems where we had what is the probability that this model produced the sequence, or what is the most likely state transition? For those two models, you know the following things. You know the pi, the starting sequence, the starting point probability for each of the states that you have. You know the number of states, obviously. And you know all the transition probabilities. And you know these BJ variables. So you know the probability that a certain state has produced a certain color, right? And with those, you can then compute like the likelihood of this model having produced all this sequence. And for that, you have to sum up over all the possible transitions within that model. And for the most likely state sequence in the model, you just compute one sequence. Okay? And we're going to get to that again. But basically, the motivation here is to know all these types of questions, or to know the answer of all these types of questions, like what's the probability that this model produced this sequence? Well, that requires a lot of computation depending on both the number of states that you have, and you know this number, but also the number of time steps you have. And the more both get, the more complex this calculation is. And so these are the 5 things that you know about your model when you try to compute the probability of observing a sequence and the most likely state sequence. So is the 5 tuple that defines the hidden Markov model. Number of states, possible observations, transition probabilities, observation probabilities, and starting probabilities. Okay. And we talked about how this can be used for classification. We will get back to that. For classification, I mentioned that we just need to calculate the posterior and each model now is trained on a different set of observations because each model is only responsible to model a positive sample. Okay, so we'll see that in a second when we talk about how to train a hidden Markov model. You'll see that there are no labels for the training, because each model is only trained on positive examples. Okay, so you never train a hidden Markov model on negative examples, because that would kind of defeat the purpose, because you're trying to model a certain type of sequence in the model, but don't give it negative examples. Okay? Alright, so the basic models, as we said, given a model lambda, and that is defined by these 5 tuples, or by the 5 tuple. What's the probability of the observation sequence? Given a model lambda, again, we know all the parameters, and given an observation sequence, we will have to find the state sequence that has the highest probability. So now, instead of summing over all possible observation sequences in this case, we only want to find the one optimal observation sequence. And in this case, in the last case, this is what's going to be new today. Basically, we're learning the model parameters, so the transition probabilities, the observation probabilities, and the starting point probabilities. So that the 3 variables that we need to update are A, the matrix, the transition matrix with the aij values, the bj values, and the pi I values. Okay? And here you see it's like what we are using is an observation sequence, or like a set of observations, or a set of observation sequences, sorry. And you don't see like that there is like a comma y or something like that. We don't need that for this case, okay? And we would like to know which one's the optimal one. So we talked about the evaluation problem, which is the first problem. So we want to know, given a certain observation sequence, what was the probability that this model has generated it? That would be like trivial if we have the state sequence as well. That's just basically multiplying those b's. But however, obviously we don't always have access to the observation sequence, the state sequence. But we can compute basically the probability of a state sequence within a model. Okay, so that's basically just computing all the transitions and multiplying them with each other. And now we can compute the joint probability of O, Q, given lambda. So if we had access to this, it would be trivial. As you can see, you just multiply those guys. We can calculate this. That's trivial, but we don't really, like, we have to factor in that we need to compute this for everything. But we can get this, which is the joint probability between the observation and the state sequence. And this is kind of like this double product here. And the cool thing now is that we can, through this joint probability, we can get at the actual problem, which is the probability of the observation sequence given the model, by just marginalizing over all possible state sequences. And that is a solution if you want to compute, I don't know, I mean, if you have 3 states and the maximum length of your observations are 3 or something like that, well, that's not so hard. But if it's like 100 and 1,000 or something like that, that becomes really, really problematic. So like there are many, many possible state sequences. However, as we talked previously, in a sense, you can reduce this as well through your these, like if you add impossible transitions, for example, right? So that's one option to actually reduce the computational load in this case. But in any case, we are using like an algorithm that will reduce our problem of having to go over all the possible state sequences, and it's called the forward-backward procedure, where we first gonna define the forward variable, which is called alpha, which basically describes the probability of having observed a sequence from the start to the point t being in state Si, given a certain model. And it basically starts off initially in this recursive algorithm with giving us the probability of starting in point I, and we have like n many possible starting points I, so we would have n of these to start off with, right? And then for us to go into the next step, we only have to look at basically what the value is that brought us here, times all the possibilities to transition from all these values into this guy. So what we need to do is we need to sum up over the probabilities of the first of these guys here, with all their alphas that we computed, and then multiply it by the respective aij, which is the probability to transition from I to j, and then multiply that with the observation probability of j to produce the observation t plus first observation. And we put that in words here. And basically, what this helps you is with you're kind of calculating everything to a certain point and you're moving forward, but you don't have to recompute this all the time. You just take the values that you had previously and multiply those in, so that severely reduces your computational expenses. All right, and then for the for the entire for the probability of observing a certain sequence given a model, then it's just the sum over all the end points. So we have again n different endpoints, and they're alpha capital T in this case. So this gives us not just a sequence of states and computes the probability of having a sequence, but it computes all possible ones by just always moving in the if you fold out the states in over time, as we've seen here. If you fold out those states over time, you basically compute this row, and then you take what you computed here to compute this row, and you compute that, so you don't have to go back and forth all the time, okay? And yeah, sometimes recursion is a bit tricky to really visualize, but if you think about it a bit more, I think that should be fairly clear. All right, and this is the forward part, and in case of the backward part, we actually, so still forward, this reduces our computing down to n squared times t, which is a lot less than n to the power of t. And now the backward variable basically just explains the other part. So if alpha tells us what happened until time t, the beta variable tells us what happened from capital T to the point t, by going backwards. So this is kind of like the probability observe the tail end of the observation sequence, given that we're in state Si and given certain model lambda. And we can compute this again recursively. We start off with the final value for all of the points being 1, and then we move backward 1 point, and basically we have to split this part up into the sum over all the j's with observing this new the t plus first observation in state j, which is our b value, right? So we sum up over those, and then we multiply that with the two variables where we have the rest, which we just said is this beta variable, times this variable where it says we're transitioning from one to the other. So we sum up, this is the same sum here, over these guys times the transition from I to j times the beta that we had before, which is this part here. Okay? And basically, in other words, tells us when in state Si we can go to n possible states, and each with a probability of aij, so we have to sum over n, sum over all the possible states that we can go to, and weigh that with the transition probabilities. And then in the new state that we end up in, we observe a new variable or a new observation, which then is the bj of the observation that we see now, and then explain the rest of the tail end of the observation sequence, which we defined as beta. Okay. All right. So now if we move on to the second problem, we have the problem now to again find the optimal state sequence. And or the most likely state sequence. And for that purpose, we define this variable gamma, which basically is defined as being is defined as the probability of being at exactly this time step t in a certain state given an observation sequence. And so we're at a time step t in a certain state. So what we need to do is we need to know the probability of how we got here and the probability of like where we're going to go next. So that's basically giving us the motivation of like why we have the forward variable that explains until exactly this point like what's the probability to be here. But then we also need to take into account the probability to transition from here on to the end, because just because this like coming here was the most likely sequence doesn't mean that this is the one from where on we can now finish the sequence of observations, right? Because there could be some zeros in there that would, or this could be basically a Kulisacker. Yeah, I guess that's the English word for it.
But this is I'm sorry, this is a purely generative process, right?
Yeah, so it is, and we don't try to like find the separation or whatever. Like this is basically just telling us like the likelihood of being at a certain time step in a certain state. That's like we define this variable. Like, it is not directly useful for us for anything, but we'll need it to compute the optimal state sequences.
Sorry. My interest in generative always kicks in.
Okay.
I apologize.
No worries. Yeah. So you can use this to generate sequences, obviously as well. But this just basically this still also doesn't give us like the most likely sequence. It just gives us for a certain point at a certain time, or like for a certain sequence, the probability of being in a state I at a time t out of this observation sequence. Okay, so that's all that does for now. Okay. Basically, in other words, like the alpha describes what's happened before. So this is until t, and this is from the end to now t, and we divide by all the other states probabilities to be in at a certain time step to keep this kind of like normalized, okay? So the numerator explains the whole sequence and the denominator normalizes the term to guarantee that the sum over all of them is 1. So what we now have to do basically is just find that each time step t, the optimal or the maximum gamma value, okay? But that doesn't allow for like a couple of issues, and we are using the Viterbi algorithm that is again based on like dynamic programming, which makes this computation again more efficient, and it's not like lacking a few issues. And in this case, we now kind of like define a new variable delta that basically is the same as the gamma that we had before, but it's the maximum of all the previous state sequences. Okay, it's the probability of like having observed a certain state sequence until a certain point, being in that point, and having until now observed these observations and given a lambda. And we utilize recursion again to compute delta t plus 1. So how do we start off with? Well, we start off with the probability for all of these points to have been the starting point with a certain observation. So we multiply pi I with bi and the first observation. And if you have, for example, a hidden Markov model that only has one legal entry point, well then you always start off with the same point. And from there on you have computed everything related to the first starting point. And in this case though, we can end up in, or we can start off in every single, like of the n states that we have in our model. In this case, let's just like keep it with 3. So we start off with this guy here, because this was the maximum of pi I times bi, okay? This was the maximum one. Now the cool thing is we can completely forget what these were. We don't need them, okay? And now we use this value, which is now called delta 1, because that's how we defined it. We use this value, delta 1, and use that in the computation of each of those points, right? But we don't use any of these other points anymore. And then we basically take the recursion step, which is delta 1, so that's the value that we just calculated here, multiply it with the transition to this guy, which is this, and then how likely did we observe this in this one, right? We computed here, here, and here, so we need 3 more computations, right? And then we look which one's the maximum, and in this case, this is the maximum, so we can throw all these now away. Like we don't need delta 1 anymore because we have delta 2 now. And then we do delta 3 and we find out that this is the guy, and then something happens in the middle. And so this is kind of like just iteratively basically summing up or like getting these values in, okay? And you can already kind of see like if these probabilities are very small, this delta value becomes smaller and smaller and smaller. Yeah?
Sorry, quick question. For in each stage, the maximum probability does not necessarily mean that stage will be in the final pass, right? Because we have to compute every path. For the
Yes, but
This is a greedy algorithm, so, right? This is a greedy algorithm, so it will not do it.
but like it doesn't. It's not always the case.
You're finding the global minimum, maximum?
Yeah. For example, like there might exist 2 passes that go to the end. Like the first pass might have like this maximum in the second stage, but the other pass might not have this maximum on the second stage. But in the end, the maximum pass.
right. Yeah.
If that's the case, you shouldn't just like ignore all the rest of the result. You should still like keep it and keep track of all the results. And then based on the last stage, you back point.
Yeah, you backtrack at the end. Yeah.
Yeah.
But that prevents you, if you keep them, that prevents you because you don't know transitions. Imagine that you find the state N that is actually lower than the state Y that you picked. Then you will need to backtrack and actually recalculate everything, so it doesn't help you. Right? If you find that state, you will not get the transitions that are leading to it. You will just know that from 1 to 2, you have maximum. But but in that case, you're back to either forward, backward, or an N to T type of calculation, which is this is so much smaller. This is almost linear. Well, not really. It's 3 times N. So that's why it's greedy, and this is why it's faster. And now finally I'm explaining something in algorithms. Yay! I made it.
So what you're saying, I think what he's concerned about is that even though this is the maximum point, in this case, there might be no way out from that location, or like there might be, but the,
Well, that means that the whole model will have discontinuities, which does not necessarily happen. Would it happen? Because if you will not have holes in this type of model.
no.
So there's always going to be something, and you will not be left out sort of standing without the connection to the next state.
It's possible. It's actually possible.
How is that possible?
Yeah.
Okay, tell me. Teach me.
Because all the transition probability and the emission probability are given. Like the maximum at the stage 2, for example, like if I have 1, 2, 3, 1, 2, 3, all states, right?
Mhm.
Maximum at the stage 2, if it assumes to be 2, does not necessarily ensure like this stage 2 at timestamp 2 will always happen in all the passes. Because like there's other paths that can, like for example, the transition probability from stage 3 to stage 2 is way bigger than transition probability of stage 2 to any stage 1, stage 2, stage 3.
Yeah, that's a problem, but
So what you're saying is it will still find the end, except it might actually not be the optimal.
yeah,
Yes, but what I'm also saying is like it shouldn't be the greedy algorithm. Like we just ignore all the results at each timestamp. It should be we pre-compute everything and we based on like at each we keep track of the previous.
right, yeah, that's true, yeah.
But there's a logic in using Viterbi algorithms because there are many processes that are really time sensitive, and there's really
Yeah, no, actually.
and you're
yes,
looking for
yeah.
one, you're not looking necessarily for the one.
Well,
No, I think you're right. So basically, you compute the probabilities at each step, and then once you're at the end, you basically follow the most likely path back. So you're not like throwing them away. You're keeping the values. So, but you keep the deltas for all the values at each state. So it kind of like increases. Yeah, you're right. Sorry, like I completely messed that up. You keep the value at each time step in the memory, and then at the end you walk back. Yeah, that's correct. Because yeah, otherwise you could have these issues.
No, I don't get it.
So you compute delta 1 for each of them, and then you compute delta 2 for each of them, but you only use the maximum of the previous one
Okay.
for this state.
Right.
So that's the point. You're not just taking this one, but for each step you're only multiplying it with the maximum one that leads into this one, and not the other ones.
Okay. Yeah.
Yeah. Sorry, yeah, like, I should know this. Okay. I hope everything has been unclear now. And so, yeah, we can take a 10-minute break and then start off with the even more complicated one. All right.
How are you doing? Better? So we cannot fix my GPU that surface. So
Yeah.
I finished my robotics last night. And now you reinstall Linux and try again. So that's what I have to do. So the movie is actually really good advice. The key use small sample, just to check if the algorithm
I guess I could do
and then use their server
classification to see like
to run it.
how well my generation works, but I guess, there isn't really like a foundation set that I need just with my training data.
Yeah, so, what are you generating?
It's interesting.
I'm still trying to decide what to generate, but I kind of want to try to generate, like, modify, using GANs to like apply some type of effect, like maybe like.
I think what you could do is, you could
So these are kind of okay, it's still recommended.
evaluate, like if you have like pictures that look similar to something natural, you could, for example, ask people to rate it on like a scale of naturalness.
Oh, like do some type of evaluation,
Yeah.
like on the
And
calendar.
Yeah, or like with the
Like the grass becomes wall and everything, so it's,
They think it's like a real
we cannot do it.
right.
Or Rio or
We
like
still
generate.
have
Okay, yeah, that'd be
a
pretty good.
smaller
No,
file size,
that's one
because
option.
it's great.
I was thinking of maybe like even using another classifier to, or like already like pre-trained classifier to see if it can like,
Oh, okay, you put it in the main.
or some type of like captioning thing,
Well, what
to
number?
see
Yeah.
if they can actually detect that the
I was
changes.
looking into my camera, I didn't see.
Actually, like one other way to
There's
do
on
it
the main page. Is it number 10?
would be, you could look at,
You see
first
that
of all,
on
like
the-
one of the things that I would also plot is kind of like the
You see that?
generator loss and the student loss, how they look like.
So maybe we should start.
Is there any like parameters I need to use on?
Yeah, I just saw it too.
Yeah, I mean like
For
network size, if you use an
network
MCN,
size,
for
yes.
example.
Well,
Okay, like number of
Hills.
layers and
Image
stuff.
magic,
And then,
which is.
so you can use that and look at like your
I feel so bad.
loss
All my
curves, like
years I
if
did
they're
not
going
know.
down properly.
I went to
So I
Twitter,
would plot this and put that in
I don't know if you know
visualization.
Twitter, you ever?
But then also what you could do is, for the generator, you could look at
How do I
like
crop to the mat?
They had,
How do I crop to the border?
they were trying to
how
explain
confident it is to
how
have to
they're
do
doing
like
their,
Ah, that's different.
values,
So,
Just the
how they
it's
improve
different.
their, using machine
Ah,
learning,
this
how
is
they
because it's
improve
black and
their,
white, it just goes
pick up
white,
the
white, 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 black.
to get better,
And that's easier.
to
And then fitting it in is easy.
decipher
You
between
can probably
good,
set
good,
that.
good Twitters and, just for good people that are.
for a
You can
variational
check
autoencoder, you
comments.
could go like,
The,
you could look at
Something.
the
MATLAB is actually
probabilities
Yeah.
at the
Now, I
output,
think send you an email said that,
or like,
well, these are,
Yeah.
these are masks, so what you would need
But
to
their
find
team
is,
I don't know if you wanna
masking.
work with them. Do you guys like Twitter? I mean, not Twitter, but
yeah, I think you would,
Because yours is a different color, right?
yeah,
They have.
Yeah, but you will never know.
and this is like
Yeah, this-
a big
well,
problem there anyway.
this is why you need a
That's
classifier,
fine.
right?
I guess
But,
what you could do is just
image,
plot the
using
losses,
binary mask,
and then
Hey,
have
Can
some
you
guy,
these
some
things
person, I wanna
in
ask,
MATLAB,
the lady.
if it's not
this is
red,
like how natural images look like, this is how the
I
generated
found
Somebody
ones
one
wrote
look
a
like.
girl, a lady by
It
name
looks
Diane.
fairly
so you
similar.
create a mask
You know,
and
if
you
we
will
can
pull it
gauge
out.
ourselves, to see if
For
that
one,
makes sense or
manually.
not.
But,
As a comparison, you
it
could do an
may be-
autoencoder to try to do the same.
This is
and
why
see
you,
if
this
it
is why
doesn't
you
work.
wanna do this, right?
Yeah,
You were asking about,
but,
yes, the
the job,
um,
was it for the summer or?
I think,
Yeah.
I think it's just,
I'm
you
not
should be
sure it's
fine
not
with just
like
like,
that job.
like plotting them and like, I mean, if they really look kinda natural,
doesn't
or if
look
they really
like
look
it.
not
Right.
really
Well,
natural,
that's what
kinda,
Yeah,
like what people will say about
Yeah,
it,
yeah.
so we don't
I
really
don't,
have to
well,
comment
but
much
when I
on
open
it.
it in MATLAB, it
But I
shows
think
me
My question, I was
that would
asking
be one way
so
to
that's
I
how
was
I
sending
know.
an email, 'cause I found her
then
name.
I'm okay.
I was gonna ask you,
and
I need to
like-
Because it
ask you
gives
first.
me.
Am I allowed to use
What,
like pre-trained models or anything like that,
Are
or
you
Which one?
like follow
This is
certain
one,
Are you
this is-
tutorials?
I put
or
copy
would
of them.
you rather do
This
an
could be
internship?
generated
I mean,
these
where
things
is
or got
that?
the right
I
entire
need to know where you
No, you
stand.
can use,
Oh, no,
like,
you have newer ones, the newer
a trained
ones.
GAN model,
And what-
So
or like
for
a
the-
script, but you should train it yourself, I think.
Not the entire,
And,
but the
uh,
newer
I
ones.
mean, you don't wanna, cause right now right now you're in.
Yeah,
Because
because
when
like,
I see
I
when
think
I
you should
open-
just like try to use GANs on
Would you rather do
this
internship
data,
found in
that would be,
and then like
But
the hard part
maybe
is just
just
like
think
finding
you're
just
fine.
yeah.
Maintain some servers
I
and
know that
data center.
the discriminating
what do you go about, just get some money?
And you could try to use,
I haven't
like, the discriminator that is,
No, don't worry about
like
that
one
one.
of the hidden
But
layers of
my
the
question
discriminator to
in
do some
general,
classification.
just contracts.
Could try that.
I'll try.
So
Because I just wanna
to
Okay.
kind of compare,
Would
oh,
you
what does
like
the CNN
work
do,
like 6
what's,
months just to do something?
we had that
But the
in a paper,
problem is that I don't have
recently,
a long time.
Yeah,
I was gonna talk about
How long,
soon, I
well,
guess.
you went back to the
So what we did here, we had a DC GAN, which is kind of like this part, and then we use the final convolutional layer as an embedding that then goes into like one fully connected normal layer, just a feed-forward layer. And then we did some classification on top, and we found that if you just use like a CNN, so that's kind of like just the discriminator part and this layer of classification,
Oh, you have a
you're
good-
not as good as if you use like a DC GAN to do that.
Are you
So
sure?
you actually use the DC GANs in classes?
That's
Yeah.
good for you. That's actually.
Like not, so in the classification, so this is, you only use the generator
Machine learning.
in the training phases. In the classification phase, you cut that off, because you only have real samples now that you want to classify. When you would have kept those real samples completely out from the
Well, timing is that guys don't have time to stand cutting, timing is.
like try to.
Yeah, I was just
Like
wondering because
20 questions.
like my problem is.
And each question is like 8 hours.
Yeah.
Yeah.
Really
I was just wondering what you wanted.
Yeah, I would say like, try to, you know, try to be a little creative about like how to evaluate it. Maybe you ask a couple of friends to evaluate it, their naturalness or something, but you can also just like,
Like put it with like real pictures.
yeah, this is a real picture, this
Oh, so you're not leaving, you're not going
this
down.
picture.
You know what?
And then another cool thing that you do, that would be very interesting. So
The first part is going to be handwritten because.
basically, so you have the DC GAN model,
Typing.
you're kind of starting off,
Okay, alright, so you're here then.
so you're starting off with this variable here, z, right? To generate images here, okay?
I don't know what
Like,
you're saying, I
however
don't know
many
what you
layers, in this
got,
case
I
we
mean,
just have two
my
layers
point
that
is just
deconvolve this
letter copy.
fairly small vector into like a picture,
Okay,
right?
so what I'll do
That
is,
could be,
okay,
for
so I'll
example,
send
dimensional.
your email to
So
her.
like usually
Give
you
her
just
either
have
your
100
contact
dimensions,
and
and then
so,
this would
because your
be
contact
usually
involves the telephone number.
like 64 by 64, right?
So what I'll do is, I'll just
So
send.
way
all
more
your
than
stuff to her,
this,
so
Okay.
obviously.
he's in computer
And
science,
so,
right, that's your
what
major.
you could do here, which I think would be
And right now
interesting,
he's focusing on machine learning.
is if you
But I haven't sent nothing to her.
kind of like
Yeah, did you see?
Later
Sometimes
today.
it's that big.
I'll.
It's like
play around with the size of the file,
Like you suddenly
Okay, do that. That'd be perfect.
and
That
then
way I can send it right to you.
print it, it's 2 pages.
so like it's a bit hard to like visualize it with 100 dimensions, but if you think like you only have 2 dimensions, right?
Sometimes you
You
practice.
normally sample from
Because it's from
That you
2 dimensions, you're gonna get like this Gaussian, right?
it is somewhat,
So it's, and
somewhat
these are always
Practice what?
so I can scale it down.
Machine learning?
like mean
What is
0
that?
means distribution 1, so like this would
Yeah,
be
what is
0,
it?
Just
0,
regular
like 0,
computer science,
0, you
the software engineering.
system, right?
Okay.
And then this would be about
No,
like
it's
1
fair.
here.
But
And yeah, and those jobs.
So what you could do, and I think that would be very interesting,
Whenever you're in software engineering.
is like in
you may
training
put
you
on a
randomly
project
sample
just in
here.
a database for a while, then you make
Including
your
the
own
books.
project.
So and like you have your discriminator off to this side,
Which is great.
like the 2 trained together.
Or you may do Python
And
for a
once you're
month,
done
or 3 months.
with training, you only use the generator.
When they hire
But
you,
now
you don't
instead
know
of
really what
randomly
you
sampling
You
here,
may get on a project
you sample
where you
from
do know
here,
what you're doing.
here,
You get-
here,
you get those,
here,
they'll tell you
here,
exactly-
here,
This is exactly what we're doing.
and you
This is
really
what
just
started the
look.
project, and
Like
we went
you
through
just
the
say,
team, and
these are my values now, like you predefine your values
or just X
and
amount.
move through this latent space in a controlled fashion, so you kind of like walk along the manifold and see what this guy produces. And then you can do in like,
You want
Is it hard?
You at least be there for a year.
like get this
Now,
type
do you
of
contact?
No, so
You
this,
say,
like,
look,
if
I'm
you
not there,
just
and
train
they
the
contact
standard
this month,
DCGAN,
and I did the type through the type that went on to another conflict, so you don't have a lot of time.
like, could I just
So-
actually?
yeah, so
That's
the
what-
generator,
I don't know what she, I don't know what she does now,
it
I
gets,
have no idea, but
it
I do know
gets
it
this
relates
variable
to
C,
science, like, the last time she told
and
me,
then it
she wanted me to go out
basically,
there, she wanted me to go
decompose
out to
that. So
China.
first it does a fully connected this one, so this is not a
um,
DCGAN, this is a
And
DCGAN.
I think I will be a perfect match for
Yeah,
Diamond
it's
something,
good.
where it's
Yeah, okay, so first it has a fully connected layer that
way out there,
changes this
Right,
guy's dimension,
probably
like making it
Lancaster,
a little
that-
bigger,
Ten
and then it does,
And
doesn't
basically,
and she wanted me
it
to,
looks like it's not,
Yeah.
no, it does convolution, so another layer of fully connected, so it has two forward ones, and then it has a, like a deconvolution,
someone had to
basically,
back
okay?
up the software.
And
And she had to
So-
use the tape.
So in this
Now
one,
Remember that 8-inch tape reels, I was telling you about that, she had the,
you are,
so I told her,
where is it?
about this stuff, yes.
Yeah, here.
So there
But
will be
This noise sampler is
That's
used
And it's
in the
actually
model
why I
to
wanted to
fill
we had another
that latent space variable
colleague
that
that
then
makes
generates
focus on
this.
hoping
And instead of noise sampler, you would do
I
No,
a
seriously.
class control sampler,
No,
and you copy this whole thing, and then you basically have a for loop in here that returns
now I'm such a
predefined
good
positions.
You will be surprised.
And then you just look
I
at
love
the
MATLAB.
generation of the same.
Remember?
This is the sampler, like the result generator.
Hours,
So the
yeah.
noise sampler here
You know, slowly, slowly.
produces the initial seed,
I had to
where the
program
DCGAN
yesterday
now
to program
produces
C,
uh,
and I was like,
like
oh
a-
my god,
like
I
an image
don't
from-
remember
okay.
malloc.
So,
I need to push.
and
Yeah,
it's
I
because you
forget,
need to
you know.
get like, so what
No,
this
you-
actually
you're better
attempts to
than me.
do
This
is you sample from this latent space that you don't really want to define how it looks like, except for the fact that you want it to
Draw
be
figure eight.
mostly like normally distributed in like as many dimensions as you want to. But because you sample from this space uniformly, you get this nice
felt like that was
manifold
more appropriate
space
for me to
of like
ask
whatever many dimensions, but it's smooth.
to send you
And so you
something.
can walk along this, if you trained long enough, this manifold becomes smooth. And each point in this manifold generates a picture, right? Because
Oh, is that
after
Whisper?
you sample here randomly,
Oh, yeah.
the weights and everything is predefined.
Yeah, they have a
There's
bunch
no
of,
dropouts, there's no like
The jerk
randomness
is
in
too
the
high.
generation,
you know, but
right? You can
you
have
don't
structural
hear about
training,
Whisper at all.
but in the generation you should do that.
You don't hear
And once
about
you're
them at
done,
all.
In between, you just saw.
And so like it will
You don't
produce
hear
a
about
picture,
them at all.
but then,
It's only-
like you're,
You don't even hear them.
so
You know,
basically instead of like just
they're-
randomly producing pictures,
No
you
commercials,
want to control
no,
to produce pictures, right? And what this would do,
They're,
for example, in
go like an underground.
in MNIST would, like if you're here,
People
for example,
the comments can be pretty-
produce a zero, right?
Yeah.
And if you're here, you
Put it-
produce like
You
a
had
little
to
bit
make
of
a
different
comment
shaped zero,
that
and then you
was
produce
not
another
for
little bit of a
difficult
different
for
shape zero,
and-
might
and
become like a
untraceable.
one at some point.
They
So,
would-
so
they
the,
would
this
close it.
manifold is
But
kind
the
of
fact
smooth
that
and you
that-
can walk along.
It
Finally,
could involve in
This, for
hurting someone
example,
or
Yeah,
destroying
and just
someone or
generate,
causing any damage to someone's reputation.
basically,
They may not produce it.
you could
But what
try
they
to
do is
understand what a certain
They,
dimension
they
in this
come right up
manifold
to the
means.
edge
slow.
So
of where
in this
it's legal
case, like
and where it's
the
not.
two dimensions
And the people, you know,
were
know,
giving you
can voice their opinion
like
without,
a change of style into like different numbers and stuff. Might be smooth, it might be not
attention to
smooth.
themselves.
And then in
by
like
calling
if you
something. But
generate,
that's just,
I don't know, like animals,
That's
might
only
be
one,
that
no. I
in
saw
one
the other
location
places
of this
like AT&T,
latent space you
and
have
with other places that.
animals with 4 legs and then the other one
They're not all-
It's good, thank you.
I was actually thinking of using this more as like some type of like style transfer.
Yeah, that would be,
And then,
yeah.
but I think I could maybe still do
Engineering, precise, what else?
something similar to what
Yeah,
you
yeah,
said,
just
like,
just try to be creative of like how to evaluate it. And definitely like make it generate some stuff and save it, like they usually all have the ability to just save the data. And then just basically copy whatever they use in the generation part for like saving the image, where they use the random sampler, and just make it
What is that?
make it a non-random sampler. I guess
Oh,
it's
you know it now.
here.
It might be a good mix because they will not be able to get somebody who knows both and understand what is happening.
Yeah.
So that's what.
Yeah, so here. So whenever like you have 100 steps, you would sample, and then basically feed that sample into your in this case BX.
Some other professions.
So X underscores is the generator.
Or you may talk about maybe the president.
Yeah, it's a generator net. Okay. And so it feeds this into the generator net, and then you like you make it an image, you plot the image, and save it, right?
So that's a better bet.
But what you would do now is instead of doing like this, you would give it a predefined set of probabilities and just see what happens. And then it generates these pictures, and now you can like maybe see the style change.
I see. Okay.
Yeah. So instead of randomly sampling at this point, you like define your sample. Yeah. So and then like here you train this little loss part, and once you've trained 100 steps, it's modulo, right? You have trained 100 steps. Let's stop here. Let's generate a couple of images and then go back to this.
Look through all,
No problem.
Search for and all this information that you put out there. That's the state. And you may not get hired. So you got your conflict work.
Okay, so
Yes.
now we're moving on to basically the third problem in the hidden Markov model basic problem list, which is like how do we end up with a learned model lambda. And in this case, what we want to find is lambda star, which is the one model and with all the parameters, the BJs, the AIJs, and the pi i's, that has the maximum likelihood of maximizes the likelihood of the training sequences that we observe. So we have capital K many training sequences available to us, and what we need to do is we need to find the model that has the optimal parameters for this training sequence. And for that purpose, we introduce a new variable xi, I don't know how to say that in English, but anyways, that variable has the probability of moving from state Si to state as J, given a certain observation sequence and a certain model lambda, and this variable can be broken down into the probability of ending up in this state times the probability to move into state J times the probability that state J produced the OT plus first observation, and then going from there on out into like any other state. So that's the beta variable. Okay, and then we have to normalize this to like keep the probabilities in check. Okay, so that's a variable that we're gonna have to use later on. So the Baum-Welch algorithm is basically a special case of the expectation maximization algorithm that we have talked about before. It's basically split up into an expectation step and a maximization step. In the expectation step, we calculate both the xi and the gamma, given our current model lambda that we have, and obviously if you just start, you would randomly initialize all your variables and compute it from then on. For the maximization step, we now then compute the new model parameters given the xi and the gamma variables. And as usual, we iterate those steps for a couple of times until convergence is reached. For the expectation step, we need to introduce 2 more variables, which are basically our indicator variables so that we can count properly. And a ZIT basically is a 1 if we are in state Si at time t, and 0 otherwise, and Zij t is our soft count for, or like allows us to count how many times we move from I to j in any time step. Okay? And yeah, so basically these allow us to find the soft counts and how many times you transition from one state to or like into one state, Si, and how many times you move from Si to Sj. And obviously this will need to be normalized by the total number of times that you end up in Si, for this one, for example, and the other one is like the where you have to normalize for total number of well, it's kind of like gives you the number of times you end up in Si. All right, so for the expectation step, we have to compute the expected number of transitions. So like how many times we transition, and the expected number of times of transitioning from state Si, and that's basically the sum over the gammas. And our maximum estimation for the transition probability is the ratio between basically how many times do I transition from I to j divided by the number of times I am in I, and then the probability of observing something in j is obviously the number of times I am in j observing this divided by the total number of times that I am actually in j. Okay. And for the maximization step, we can now compute, we basically just have to add these sums over those previous ones where we want to sum up over all the k transition, the k observations that we have at our disposal. And for pi, we just count how many times we start off in I and divide it by the number of k transitions. So basically, to take away is what we want to understand here is based off of like a set of observations that we have access to. We basically want to know based off of these variables that we discussed before for the other problems and the variables here that we want to count at how many times we believe we transition from one to the other, and that basically gives us our transition probabilities, and then we want to count how many times you observe a certain observation. And for example, this one often ends up to be like a Gaussian mixture model instead of just like having discrete observations. And yeah, this pi I might be trivial because we might actually define only one variable to ever be the entry point. Okay, so this kind of like is the main novelty, and this would be again kind of like a Gaussian mixture expectation maximization that we had talked about before. Okay, then there is another task that you could imagine to have in hidden Markov model learning, and that would be kind of like a more interesting or more difficult one, where you would have a state sequence or a set of observation sequences, and you would want to identify like what is a likely model to look like, or what will a likely model look like. And if you really have no information whatsoever on like the type of observations that you are like have been handed to, then you would try to validate, like, okay, what kind of hidden Markov model would work best? Do I have 3 states? Do I have 5 states? Do I have 1 state? And so on. And so you would have to validate for that. If you kind of know what's in your data, you might want to like come up with a basic hidden Markov model like this one here, where you, for example, know that there are maybe only four states that I would expect to have in my data, because it's like typically you would have, so if you know it's only 3 states, you know, okay, there's like an onset, there's a maintaining, and then there's offset, so you would say, okay, yeah, there might be 3 states, but maybe you have, like, you know that there are probably 4 states in my data, you can have 4 hidden states, but then you know, for example, that you never would go from the 4th state to the 1st state, so you would not allow there to be a connection between those, and so you would just have that connection to be zeroed out in your probability matrix of the transitions. So you can come up with different types of hidden Markov models, but learning from the data directly, like what is the most appropriate sequence, or like most appropriate model for your data, can be very tricky and difficult, and I would not recommend to try to find like automatically the topologies, but like try to use kind of like top-down information to choose which model would be best. Okay. Yeah, so and often you would want to kind of like validate for the number of states that you have. So do I just use 3 hidden states? Do I use 4 hidden states, and so on? You can try to validate for that. Okay, that's it for hidden Markov models, and I'd like to start a little bit of a new topic before. A little bit of a new topic that some of you have already seen. But before we go to the deep learning stuff, I wanted to basically kind of introduce another concept which I'm quite interested in. It's basically a multimodal or multi-classifier machine learning, where you don't just use a support vector machine or a hidden Markov model or a whatever model to learn a certain concept, but you learn many different classifiers and try to understand how they, like, if you combine their knowledge, if you can improve your classification performance. And the other part is you're using different types of modalities as input to classify as well. So sometimes what I often work with is acoustic and visual data. So like human behavior often can be like split up into like multiple categories. So you could have the behavior that you see, the behavior that you hear, and also, like, for example, we consider for like the language, the words that I'm saying as a different modality as well. So you have like the verbal modality, the non-verbal modality, the visual non-verbal modality, the acoustic non-verbal modality. But then you can also, like, if you want to, you can split up the visual modality into multiple ones as well. So you could have like the facial expression, one modality, and then my body, posture and gestures, etc., as another modality, and so on. So there's many different ways to do this, and I would like to like kind of motivate how combining multiple learners can be of interest or like importance for some of our work, and I have a few examples.
Silence! Yes! Remember, you're never going to be able to completely stop talking.
Jerry, 94% of communication is nonverbal.
Here, watch. Phil's reaction to hearing about George's man love for a ginger. Shut up! Shut up! Shut up! That's the idea! Raymond, there's no way you stick to this. Oh, you're gonna start now? That's right.
Anyways, so it's just a kind of like a brief example of what we do not mean with nonverbal communication, obviously. But and so nonverbal communication really is mostly like facial expressions, the tone of voice, and I have another example here which I would like to play for you to see, like, or to motivate like how knowing about other like angles or views onto the same topic can give you a better understanding of what's going on. So for those who know this example, quiet. And for those who don't know the example, we'll first look at the written modality, and then we'd like to know if you guys know what's happening. Then we're gonna listen to it, and then we're gonna view it, and then I think it becomes more and more clear what's happening. So the red text is spoken by the woman who is a newscaster, and the blue text is spoken by this guy here, whose name is actually Guy, which is kind of funny, and he is in the TV studio live on TV. So. Music Online, Guy Cuny is the editor of technology website News Wireless. Hello, good morning, good morning. Were you surprised by this verdict today? I'm very surprised to see this verdict come on to me because I was not expecting that when I came to, it told me something else, yada yada, big surprise, exactly, yeah. We got the cost that is involved. Do you think more people would be downloading online? So it's kind of like this weird conversation. We don't really have like a lot of context of what's going on. So let's listen to it, like how this sounds when we listen and read to it.
Mean for the industry and the growth of music online. Well, Guy Cuny is the editor of the technology website News Wireless. Hello, good morning to you.
Good morning.
Were you surprised by this verdict today?
I'm very surprised to see this verdict to come on me, because I was not expecting that. When I came, they told me something else, and I'm coming. You got an interview there, so it's a big surprise anyway.
A big surprise.
Exactly.
Yeah. With regards to the cost that's involved, do you think now more people will be downloading online?
Actually, if you can go everywhere, you're gonna see a lot of people downloading to the internet and the website everything they want. But I think it's much better for the development.
What's going on?
You know,
It's a taxi driver.
oh my god.
You know it.
You did it.
So
Mean
anyways,
for the industry and the growth of music online. Well, Guy Cuny is the editor of the technology website News Wireless. Hello, good morning to you.
Good morning.
Were you surprised by this verdict today?
I'm very surprised to see this verdict to come on me, because I was not expecting that. When I came, they told me something else, and I'm coming. You got an interview there, so it's a big surprise anyway.
A big surprise.
Exactly.
Yeah.
yeah, so the guy had no idea that he was going to be interviewed. He was picked up, so like they were looking for a guy with his exact same name that is like the editor of Music Online. But so we kind of like it should try to help to illustrate that like if you have information that comes from different views onto the same kind of instance, you might be able to like derive more and more information and try to understand the actual context of what is going on. And so this is kind of like called, or is like some of the challenges of multimodal human communication dynamics or machine learning from multiple modalities. And a couple of things that we need to do is first we need to be able to track and understand, or like track the behavior, track the facial expressions, know when a person speaks, how they speak, characterize that. Then we need to do temporal dynamics, computation. We need to understand like what the sequence of behaviors mean, and you could use, for example, hidden Markov models for this process. Then we need to, and this is kind of like the focus of this exercise today, then we need to understand like how we can actually combine the information through multiple classifiers. So you could have a classifier that's just listening to the audio, you could have one that just views the faces, and so on. So you want to try to understand like how do you able to like combine this information, and you might run into like various difficulties. So for example, facial expressions and voice and gestures don't actually happen at the same time. Also, your sensors produce observations at different time steps. So for example, a camera has like 30 hertz, while like a person, like a microphone produces like 16 kilohertz output, or like even more output, or like faster output. So you have to kind of try to understand, okay, what is the right way to split up the data so that you can conduct some information fusion there, and then you have to obviously try to understand and interpret what's going on. Just a few things that I'm working on. So we're working on the visual domain. We are interested in gestures, body language, proxemics, facial expressions, eye contact. In the verbal domain, we're interested in like what words you're using, what the words in a context mean. We also like are interested in like how people change their vocabulary with regard to like certain situational changes, or like if an individual has like is highly emotional, do they change their vocabulary, etc. And then we're also interested in how the acoustic changes, or how the acoustics change when the person has certain characteristics. And these, like what we're trying to classify based off of the visual, verbal, and acoustic domains are, for example, emotion. We want to understand the valence of the arousal, or the anxiety level, or the happy, angry, sad kind of type of emotions. We then also are interested in like trying to understand if two people that are interacting with each other are engaged in this conversation, or if they're kind of like not so much involved. We want to understand how people form rapport, so that we can use this information to generate or to build computer programs that are actually building rapport, or are engaging, and facilitate that. We're interested in trying to understand like how conversation works, and also like what the verbal content actually explicitly provides. Okay, from like kind of like the sensing or the start point where the cameras and the microphones are, you can also kind of like define like an axis of what we have to do, and so we have to first use the signals that we get, and then which are like from various different sources. So we have like connect information, we have facial expressions, we have acoustic analysis capabilities, and for example also physiological analysis capabilities. And we first track facial expressions, or the face itself, in videos. We then also try to like temporally integrate like the location of the face. For example, if I just see the face like this, I don't know what there's a gesture in the face, but if I see a sequence like that, I know that that is a nod. So you like integrate the information over time to like basically define, okay, so I've now observed a head nod or a head shake, or I've heard that the pitch is going up or something like that. Then I want to integrate my information multimodally to better then understand what the context is. This is just a slide to show a little bit of like the challenges that we are dealing with. So for example, it's not very easy to kind of model the dynamic processes that you see in human behavior. There are sometimes, like the interesting part sometimes is to basically look at the synergy, or like the synchrony between what you're saying and the facial expressions that are common or like associated with those, But for example, in my work on basically like the assessment of well-being of individuals, one of the symptoms or the things that we observe that is quite striking sometimes is that the verbal content is kind of disassociated with the facial expressions and the voice. So sometimes you hear that the person is saying something really, really cruel and terrible, but their facial expressions are completely flat, for example. And that is the case if the person sometimes, for example, doesn't really process certain issues that they have, and like so, the multimodal synergy is an interesting task here. And then obviously we have sometimes problems with like integrating over multiple cultures, and you need more and more data, etc. But machine learning can help with all of these kind of challenges. We work on the medical domain, educational domain, so we try to teach people through these algorithms, and then we also use that to better understand like game theory and negotiation tasks and so on. Okay, so that's kind of like just an overview of like where you could apply this multimodal stuff. Let's go into like some examples. So in this case, we have this guy in a cowboy hat, obviously, and what we can observe from this person is we can listen to their voice, we can look at the words that they're saying, we can derive something from their voice, which in this case is the pitch, which you see like it rises and it falls off, or in this case again it rises and falls off at the end. And then we can also kind of discretize his behavior in like the visual domain. So we can say nothing happens here, but during this part he looks at the listener and then nothing observed there. You could add many more. You could have, for example, smile here. You can have person smiles, doesn't smile, smiles. Or you could have like a continuous value of like a probability that you believe that the person is smiling or not. And then you can already kind of see some of the difficulties that we're going to have when we're trying to combine all these signals into like one decision. So first of all, the person's talking here, and then that's a continuous signal, and this is also a continuous signal, but then we have like a couple of words here which are discrete and like are limited in time, and they're not synchronized between the two, because this is continuous, this is not. And then we have this other thing here which basically starts whenever there is no speech, and then like it continues for a while. But so we need to come up with ways to be able to combine these different sources, different types of data sources in a fusion. And in particular, this is kind of like what the difficulty lies in. Like, how do we combine all of this to then get that affect, confusion, engagement, etc., all these other variables that we had. And you might ask, okay, so why don't we just use this to make the assessment, or why don't we just use that to make the assessment? Well, there are kind of like a lot of opportunities. So, for example, I think there's like this fantastic advertisement that I should brought. Which one was that? I think it's an Allstate advertisement, where basically, I'll try to find it. It's kind of
This
like,
is my car.
yeah.
This is my car, right?
Whatever. So basically, the person comes back. So there are two people. One person comes back to a car where there's no tires on the car anymore.
Oh yeah.
And like it says like, "Are you kidding me?"
Yeah.
And then the girl gets a new car, and she's like, "Are you kidding me? That's awesome!" And so basically, if you just had the words, "Are you kidding me?" you don't know in which scene you are. But if you have the facial expressions, the gestures, the context, even the car, how it looks like, you get more and more information to be able to disambiguate what's going on. It might make you more robust to noise. So, for example, if you're interested in identifying if a person's happy or not, but the person's like this in a moment, but like they're talking in a very happy voice, but you don't see that their face is smiling because there's actually something occluding their face, you can infer from the other modalities that they're still happy. Okay, so that's another option or an opportunity here. And you can use this also kind of like to try to disambiguate or better learn hidden dynamics within a human's behavior. So there are a bunch of opportunities through this fusion, and one example, for example, is like the audio-visual speech recognition, and we're going to talk about like why this did not actually work out that well in the past, but you could imagine that you want to recognize, and I think, who was that? DeepMind, I guess, just came out with a new lip reading neural network, which I think is kind of funny, and I hope it's not going to be used for bad things. So basically, you can use the acoustic information plus the visual information, so maybe the lip reading used to better guess what kind of vowels or phonemes are being spoken, and then maybe you can better understand what the words are. This was not super successful, and we'll probably talk about why this was not super successful in a little bit. But in principle, to combine information over multiple modalities, you have multiple options, and the most extreme two options are to combine all your information sources into one feature vector before you then have that feature vector go into your classifier. So you need to learn one classifier, but that has a large dimensionality as input. That's the early fusion. The other option would be to learn for each modality a separate classifier, and then later on make a decision on like what this ensemble or this group of classifiers believe. So the fusion kind of happens later. So this is called early fusion, this is called late fusion, there are things like intermediate fusion, and we're going to see that, for example, you don't just need to like make a decision like maximum or sum or average or whatever here, but you could actually also learn this. So this could be another classifier, but obviously you need more and more data for this. The rationale for learning multi-classifier systems basically is that there might be, you might actually be able to learn a ensemble that actually works better than every single classifier separately from each other. And you can imagine that, for example, you can learn. So you can learn from each other. So if you have like for example you learn for a test, and everybody kind of knows a little bit of a different information. So like to learn from each other can help as well. So and like the sum of all the parts might actually be better than like every individual classifier by itself. And so what we want to do in this case is kind of like learn many classifiers that in the end have a better or a more accurate opinion than every single classifier by itself. Okay, so some of the things that you could imagine, for example, would be like a similar an analogy to this. Obviously, is like why does the Supreme Court have 9 judges, or actually currently like 8 judges? Because obviously you would trust a group of people that are very accomplished and have their opinions might be more accurate and more fair than just having one single individual with all the power to make a decision. So that's kind of like also going into the idea of like why we have why there are multiple classifier systems. But there are a couple of problems with that associated as well. So for example, if you learn multiple classifiers, you don't just learn one set of hyperparameters. You don't just have a support vector machine that has one C value, and you don't have just one neural network that has like one or two layers, but you have maybe like 5 now, and you have to like validate each set differently. And each classifier might have a different topology, different set of hyperparameters. So your search space becomes more and more complex and bigger. So that might make it a bit more difficult. And there are 2 questions that we really should address before we just like naively learn a multi-classifier system. The first one is like, how do we generate base learners that complement each other? And base learner in this case is a support vector machine, for example, on a certain task might be a good base learner. It could be pretty bad on the entire task, but it might be good at a subtask of it, so that could be a base learner. But you can have like any learning algorithm could be a good base learner, but you want to find a set of base learners that complement each other. They don't know the same thing, because if they know the same thing, they can't learn from each other's mistakes, okay? Because they make the same mistakes, obviously. So, like, how do they complement each other? And then the second question that we need to address is, like, how do we combine these base learners' opinions at the end to maximize our accuracy? So that could be, for example, very simple, like if you have 9 judges or 9 base learners, you just take the majority vote. So what's like, did 4 of them say yes, or 5 of them said no, and you say no. If it's the other way, you say yes, obviously, okay? So the first question, so that they actually complement each other, we need to guarantee diversity. And diversity in this case means that the classifiers know other things about the data from each other. So everybody has like a different kind of opinion, and you can imagine that if there's no diversity, you cannot improve your opinion. And we kind of want to maximize the individual accuracies and the diversity between learners. So like each individual classifier should be good, but should be also different from the others. Okay, so we want to balance this. So like and there's like often a little bit of a caveat here. So if you try to maximize the performance on one classifier, and you don't ensure diversity between classifiers, you might actually end up by learning the same thing over and over again, okay? Because there is an optimal solution maybe for one classifier with your given data set. But how do we achieve this additional diversity? And then there are a couple of ways to do that, and we'd like to talk about all of them. So the first one is kind of like learning different algorithms. So we just had a difference between, for example, support vector machines and hidden Markov models. So support vector machines make a decision based off of like one input at a time, and hidden Markov models make a decision based off of like multiple inputs in a sequence, okay? And the same for neural networks. So if you actually have different classifiers that are then combined, you actually guarantee diversity, or like you maximize diversity, hopefully, if they have like diverse enough characteristics. So one of them is specialized for sequences, the other one is specialized for like finding a separation between the data points. And then if you don't have access to multiple classifiers, you could, for example, try to guarantee diversity through different hyperparameters. So you can have an MLP with just one layer, and then you have one that has 4 layers, and then you combine their opinions. That might actually work as well. Then you have another option where, for example, you use different data for each classifier. So one classifier gets video input, the other one gets audio input, the other one gets physiological input. So they get like different types of sensory information, so that kind of then ends up in sensor fusion or multimodal fusion. So that would be another way to do this if you have access to multiple modalities on your data. If you only have one modality, in this case pictures, you can still do this kind of like multimodal-ish aspect to it, but you would, for example, try to extract different types of features. So you could extract features relating to shapes, textures, and colors from images, and then use a classifier that only learns on color images, color features, one that learns only from texture features, and one that learns only from shape features. That would be a different, a multi-view learning classifier that sees from the same modality with different views from the same modalities. But you could also change the view onto your training data by splitting up your training data. So you have a big training set, and one classifier only learns from this part of the training set, then another one learns only from this part, and so on. And so that way you would, for example, enable this kind of different or other view onto the data as well. And there are a couple of prominent examples that we're going to talk about. For example, the first one is bagging, where each classifier learns from a different small set and a randomly selected set of the data set. And then you have classifiers like boosting and cascading, where you in fact actually, in boosting, for example, you have one base learner that produces an output, or like produces a probability and like tries to classify your data set, but it makes mistakes, right? And if one of them, or like if multiple classifiers make mistakes on data points, the data point that they make mistakes on gets more and more pulled from the data set, so that actually the easy data points are like shown to the classifier while training in less frequency than the ones that are more difficult. So that could be improving the separating hyperplane by giving examples that are close to it, or maybe on the wrong side of the hyperplane, and so on. In cascading, for example, it's even stronger, where the one data set, one classifier basically has to decide on all the data points, and if it's not confident, it sends all the data points to the next one. So like the classifier sees all the data points that the previous classifier was not confident on. And we're going to talk about those in a bit more detail on Wednesday, and that's that kind of like for today. All right.